Hey guys, so we're doing a Module 6 review. We're going to determine whether these three things up here are functions or not. Then we're going to determine whether each situation for 4 and 5 are linear, nonlinear, proportional, not proportional. 6, we're going to decide whether function 1 or function 2 is changing more quickly. And then we're going to describe a situation down here regarding SAM running at a constant rate. Okay, so number 1, let's talk about functions. Remember, functions are very similar to linear equations in that it has a relationship between x and y. So, for example, so this is your y-axis, this is your x-axis. So a lot of functions typically, they can be linear, right? They can be straight. They can have some curve to it. You know, it could go in pretty much any direction. The one thing it cannot do is it cannot just simply go at a certain rate and then just cut up. It can't go up at all in any way, shape, or form. So, for example, can't do this. It also can't do this. Right? So you can't have a part of it that goes up and down. That's not possible. Now, this one looks like it's not totally up and down, but anyways, you get my gist. All right, so it can't go up and down. So these two are not functions. These two are. Now, on 1, 2, and 3, however, 1, 2, and 3, they're not written as graphs. So it's not something you can just look at and tell if it's a function or not. So you got a couple choices. One choice is you could take these three examples, take your ordered pairs, and then plug them in and see if it creates a function or not. So if 2 is paired up with 0, if this is 2, 0, let's say this is 5, 1 and 5, 2, and this is 8, 3. So if we have a situation like that where you have basically 4 pairs, you got 4 ordered pairs. You got 2, 0, 5, 1, 5, 2, 8, 3. Well, you can graph it if you'd like. If we graph these ordered pairs, you're going to basically come up with something like this. Let's see. Let's go down to here. Now this is, again, this is kind of a not too scientific, I guess you could say. Not too mathematical because I've got no grid lines. But we're just going to make them, okay? So this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. So if I graph this, 2, 0 is going to be 1, 2, and then 0 is going to be here. So that's 2, 0. 5, 1 is going to be 1, 2, 3, 4, 5, 1. 5, 2, just above it. And then 8, 3 is going to be, see, this is 8, 1, 2, 3. So your graph's going to basically do something like this. Okay. And there's an issue with this graph. The issue is part of it goes up and down. So it cannot go up and down at all. If it goes up and down at any place at all in the function, it's no longer a function. So this is not a function. Okay, cannot be a function. The other thing is too is that you can, like we'll talk about this here in a second. You can have multiple. You can have 2 inputs and 1 output. Like you could plug a 2 in and get 0, and plug a 5 in and get 0. This could connect to 0. That would be okay. So it's possible to have more than one y, but you can't have more than one x. Otherwise, you get a situation like this. So that's one way of looking at it. Number 2. So just like what I just talked about here, is you see where there's 2 5s for y, that's okay. That can work because each one's paired up. So if you plug in a 3, get 5, plug in a 6, get 5, that's okay. All right? So let me show you what I'm talking about. So if I create a coordinate plane, again, it's kind of rudimentary because I'm not using grid paper. So just kind of approximation here. -1, 6. So let's say this is -1. 1, 2, 3, 4, 5, 6. So -1, 6 is about here. 3, 5. So 1, 2, 3, 1, 2, 3, 4, 5, 3, 5, and then 6, 5, 3, 4, 5, 6, 6, 5. So this equation or function is going to look something like that. And that's okay, because in a function, functions can have no slope. There's no slope here, right? It just goes straight across. That's all right. You can have that. You just can't have anything that goes straight up and down. So this is okay. This is a function. So again, back to number 1, you can't have 2 x's. You can't have multiple x's. But you can have multiple y's. So this is okay. But this is not okay. Okay? So basically in jest, or in summary, is you can only have one x. You can have only one input for every output. But you can't have one input for 2 outputs. Okay? So you can plug in a 3, get 5. Plug in a 6, get 5. So you can't have 2 outputs. 2 outputs are okay for different numbers, for different inputs. Okay? So that's the point in case here. All right, number 3. So number 3, just look and see if you have any reduplication of any x's. So 2, 5 is good, 7, 2 is good, negative 3, 4 is good, 2, 9. All right, we've seen 2 before. There's another 2 right here. So if I plug in a 2 and I get 5, and I plug the same 2 and I get a 9, something's wrong. So that means this is not a function. Okay? All right, so moving on. Number 4, determine whether each situation is linear, nonlinear, proportional, not proportional. So linear means it's straight. It's going to be constant. It's going to have a constant rate. Proportional means it starts at 0, 0. Non-proportional means it does not start at 0, 0. So if Joanne is paid $14 an hour, that means if she works 0 hours, how much money is she going to make? 0. Right. So it starts at 0, 0. That's where the graph's going to start. So it definitely is proportional. The question is, would it be linear? Well, if she works 1 hour, that's $14. She works 2 hours, it's $28. She works 3 hours, it's 30. It's 3 be $52. Okay. Did I do that right? Yeah. 1, 2, and 3. It's been a little. Oh wait, I'm sorry. $42. $42. What I'm talking about. Okay. Now, so it's constant. So the rate is constant. Because the rate is constant, it's linear. It's going to be a straight line. So it's linear and it's proportional. Okay? Alberto, he's lifting weights. Right? So he starts bench pressing 50 pounds. That's something he can do right off the bat. Okay, you know, bench pressing, the bar, I believe, is what, 35, 45 pounds, somewhere in there. 40 pounds, something like that. So that means he's got a few, but he probably has like 5 pounds on each side there, right? Now, he wants to add 5 pounds extra every single week. So is the starting point 0? Does he start at 0? No. Because he does not start at 0, it's going to be non-proportional. Because it's going to be somewhere else on the graph, right? It's going to start at 50 on the graph. Then when he adds 5 pounds every single week, well, it's consistent every week. He doesn't change it up, right? He doesn't say like 1 week he does 6 pounds, 7 pounds, 8 pounds, 9 pounds, 10 pounds. He doesn't add different pounds each week. It's the same each week, right? So that means it's consistent, it's constant, so it's linear. So it's going to be linear and it's non-proportional. All right, number 6. Which function is changing more quickly? All right, so we're basically looking at slope. We're trying to figure out which one has the steepest slope. This one is starting at 20, and it goes all the way down to 0. I kind of messed up drawing it here. I had no space here, but sorry about that. Anyways, it drops down 20. That's your rise. Your run is 5. So if you divide negative 20 by 5, you get negative 4. So the slope for function 1 is negative 4. Now for function 2, you're going to do the same thing. You're going to find out, okay, what is the rise, what's the run? So the rise, you can see it's dropping down. So it's dropping down 4.5 each time. 11 minus 4.5 is 6.5. 6.5 minus 4.5 is 2. So it's dropping down 4.5, 4.5 for every single one. So that means negative 4.5. So the question here is, which one's dropping more steeply? 4 or 4.5? It should be 4.5 because it's a little bit more by 0.5 more. So function 2 by 0.5 more than function 1. Okay, and then 7, last but not least, describe a graph that shows Sam running at a constant rate. Now, if you wanted to draw it, obviously you start at 0 because he hasn't run anything yet. But as he's running, time is increasing. As time is increasing, more distance is being run, right? That should be something like that, right? Should be similar to that. Now, the question is this going to change? Is it possible that he could run really, really fast and then like just get tired and then maybe slow down a little bit, then pick back up? Is that possible? Of course it is, right? We're not a machine. Sam's not a machine. He's going to tire, and that's normal. That's okay. So the key word here in this situation is constant rate, and because it says describe a graph that shows Sam running at a constant rate, it's got to be this one. So the way you describe that is it's just going to be a line, a positive line, a positive slope. Sorry, I didn't. A's close to positive here. A positive slope that is consistently rising or constantly rising. Something along those lines. That's probably the best way you can describe that because there's no numbers here. Okay? It really won't matter what the numbers are. It's always going to be positive because he's running. He's increasing distance over time. Okay? All right, hopefully that helps. I'll see you guys later in the next video. Other than that, the last thing was, I think in this review also there was another question that says, how can you use functions to solve real-world problems? A lot of different ways. One way, hopefully you've noticed, is you can compare. So functions can help you compare two different rates or compare two different, like, pay, your rate of pay or something like that. So if you're comparing, like, maybe a table with a graph, being able to understand how functions work, you can find out which one, like in this situation, changes more quickly. So a lot of that will be, you see functions a lot in trends and payments, financial markets, things of that nature. So hopefully that helps. You can pretty much use any situation that's used in this chapter, and that'll be good to go for that one. All right, guys. See you later. God bless.